Good morning, colleagues. My name is Tanki from Loretta Utando Comprehensive School in Harrismith. I'm HOD of Technical Department. I'm currently teaching Power System Specialization. It is being an honor to be with you today to present the subject that I'm taught. I don't want to waste time. We can go straight to the presentation and start our presentation today. Our presentation of electrical technology, power system. The first topic that I'm going to do today, or the topics that I'm going to do today, it is Rlc circuit, three-phase AC generation, three-phase motors, three-phase transformer, and PLC. The first topic that I'm going to start with is going to be Rlc circuit. In Rlc circuit, grade 12 revision from term 1 up to term 3. We are going to do grade 12 previous question papers. The final examination waiting in a power system, we have the topic like this. It's a marks and percentage. The marks, we have occupational health and safety, which is allocated on the paper of 200, it is only 10 marks. Percentage is going to be 5%. Rlc circuit is one of the topics that contain high marks on the paper. It is 40 marks on the question paper of 200. The percentage, it is 20%. We have a three-phase AC generation. On the three-phase AC generation, it is 30 marks. The percentage is going to be 15%. We have three-phase transformer that contain 30 marks on the paper of 200. The percentage is going to be 15%. We have a three-phase motors and control, which is allocated 30 marks on the paper of 200. The percentage is going to be 15%. We have the last topic that it is programmable logic control. It is 60 marks on the paper. Percentage is going to be 30%. Now, in this topic of an Rlc, we found this topic contains theoretically questions as well as calculations. Theoretical questions are normally a challenge and mainly learners struggle to answer this properly. Theory, questions, and typical answers. In this topic, I'm going to start with the theoretical questions, and after this theory questions, that the possible questions of the theoretical, I'm went to the calculations. Let us start with the questions that they normally ask on the theoretical questions. We have a power factor. They're gonna say define or explain the power factor. When you explain the power factor, a power factor is the ratio of the true power to the apparent power. When you talk about the true power and apparent power, let us talk about the true power. The true power, it is where a power, it is used like as I squared times R. When you talk about the apparent power, it is a total power. It is a total power of a resistance like Z. We used an impedance where we're going to say I squared times Z. The next question that they're going to ask theoretically is this Q factor. Q factor. They say Q factor of inductor in and resonance circuit. When you explain or define that, you are going to say the Q factor. It is the quality factor refers to the ratio of the inductor reactance to its internal resistance due to the resonance. I make three possible answers that you can use when you answer that question. The first one is that one. The second one is the ratio of the inductive capacitive voltage to the supply voltage during the resonance. When I talk now about the inductive and capacitive, you know when we calculate the voltage through the inductor or the voltage through the capacitor, we have XL and XC, which means it is inductive reactance and a capacitive reactance. And when we talk about the capacitive reactance and inductive reactance, it is where we found that it is a vice versa of a series circuit and parallel circuit, where we're going to say XL is equals to XC at resonance. The last one, it is the ratio of inductive and capacitive reactance to the impedance during the resonance. At resonance, we find that the impedance is equals to resistance. That's where we found XL is equals to XC at resonance. Now, another question. They say, define the term impedance with regard to the Rlc circuit. When you answer that the impedance, you explain or you find the impedance, you're gonna say the total opposition to the flow of alternating current in the circuit, comprising or consisting of a resistance and a reactances. When we talk about the reactances in that division, we talk about XL and XC. We know, all of us, XL stands for inductive reactance and XC stands for capacitive reactance. The another typical question that they're going to ask is they basically ask is describe how an increase in impedance while keeping the resistance constant will affect the phase angle and the power factor. When you answer that question, you're going to say when the impedance of the circuit is increased, the power factor will decrease, therefore increasing the value of the phase angle. If you can check here, when the impedance increase, the phase angle also increase, but the power factor is going to decrease. But when we are saying the impedance is decrease, which means the power factor is going to increase and the phase angle is going to decrease. They say define the term resonance frequency. All of us, you know the term resonance frequency. It is where XL is equals to XC, where inductive reactance is going to be equal to the capacitive reactance. There is another typical question that they ask usually. It is inductive reactance. When you define the inductive reactance, is the opposition offered by the inductor to the flow of current in a circuit, in an AC circuit. They want to say define a capacitive reactance. That one is an opposition offered by the capacitor to the flow of current in an AC circuit. If you can check the inductor, it is the flow of current that is offered by the inductor. But when you check a capacitor, it is the opposition offered by the capacitor. Here is another question that they usually ask. It's another typical questions. How an increase in the frequency of the supplier will affect the following. We have inductive reactance, we have capacitive reactance, and we have resistance. I'm going to show you later by the circuit how to understand that easier. Let us start with an inductive reactance. It says, when the frequency is increased, the inductive reactance is also increased because the supplier frequency is directly proportional to the inductive reactance. Let me show you by the circuit. The graph. If you can check here it is our graph. There is a line straight here that shows you the capacitive inductive reactance. It means when the frequency increase, inductive reactance also increase. Let us go to the capacitive reactance. When we define it or we explain it, we are going to say when the frequency increase, the capacitive reactance decrease because the supply frequency is inversely proportional to the capacitive reactance. I'm going to show you by using the graph. The graph of capacitor versus frequency is this graph, that not the straight line, that one that make a curve. We go to the last point where we explain the resistance versus frequency. It is resistance of a resistor is not affected by the increasing or decreasing of the frequency of the supply voltage. It's not affected resistance because the resistance, the graph of a resistance, they're going to be always constant. Now, I just want us to go to the calculations where we're going to understand this RLC circuit properly. Here I'm going to take the question paper of 2019 November. Let us check RLC circuit. Let us read this question. Let us start because we are going to do calculations now. Let us start with a figure 2.3 below. We are going to start with 2.3. It says, figure 2.3 below show an RLC series circuit. Answer the question that follows. If the question talks about a series circuit, all of us, we should know in a series circuit, all current are equal. It means IL is going to be equal to IR, is going to be equal to IC, is going to be equal to IR. Which means this IT that you see here, this total current, it is equals to IR, is equals to IL, is equals to IC, is equals to IL. Now, we said a series circuit, it is the voltage divider. They give us a resistor, and they give us an inductor, they give us a capacitor. They give us voltage through the resistor, and they give us voltage through the inductor, they give us voltage through the capacitor. They even give us a given here under. Now, let us go straight to the questions. Let us go straight to the question. Let us start with the question 2.3.1, where it says, calculate the total voltage of the supply. Calculate the total voltage of the supply. When we calculate the total voltage of the supply, in our formula sheet, the formula sheet is divide our formulas. If you can check, we have RLC formula where we are going to talk about series calculations, where we are going to talk about the parallel calculations. Now, if this question wants to us to calculate voltage, total voltage of the supply, the formula that we are going to use there when we calculate the total voltage of the supply is this formula of 2.3.1. It is formula of VT is equals to root of voltage through resistance squared plus voltage through capacitor minus voltage through inductor all squared. Now let us go to our circuit. Let us go to our circuit that they give us. Let us check. Our volt VT, it is an unknown. Voltage through resistors they give us, it is 12. Voltage through inductor they give us is 16. Voltage through capacitor they give us, it is 24. Now let us calculate and substitute. Voltage through resistance, we said it is 12 squared plus voltage through the capacitor, it is 24 minus voltage through the inductor, it is 16 squared. Now, most of learners ask which thing that the voltage that they should start between voltage through the inductor or the voltage through the capacitor. You can start with anyone because this square they're going to change this negative that we found here. But usually in a simple way we're gonna say start with the voltage that is bigger than the other one, the great voltage between VC and VL. Okay, we are going to take our calculator and calculate this. If we calculate the total voltage here, it is 12 squared plus 24 minus 16 squared. Our answer is going to be 14.42 volts. Please learners, don't forget to put the SI unit. Don't forget to put SI unit when you calculate. Always put SI unit, because when they mark, they're going to give you 1, but if there is no SI unit, they're going to penalize you there. Always put SI unit when you calculate. Now, let us go to the second question. That says, let us go to the second question, which is 2.3.2, where it says, calculate the value of inductive reactance. Calculate the value of inductive reactance. If we calculate the value of inductive reactance and you check the formula on the formula sheet, it is saying inductive voltage is equals to inductive current times by inductive reactance. It means here, we are going to have, let us check our given again, where it says, let us check our given, let's go there. Our given, we have inductive, we have an inductive voltage through inductor, which means we have this one. We have current through inductor. We have it on our given. We calculate this one. It is an inductive reactance. It is an unknown. It means our voltage through the inductor, it is how much. If you can check your question paper, they give us our voltage through the inductor. It is 16, which means we are going to put 16 here. Is equals to current through the inductor. The current through the inductor, I said is 3 because I said to you the series circuit, it is a voltage divider. It means in a series circuit, IL is equals to IC is equals to IR is equals to IT. All current are equal in a series circuit. It means our current through the inductor, it is 3 amperes. Here on the current, we are going to put 3 times by inductive reactance. Now, we only want inductive reactance, not 3, which means we are going to divide by 3. According to the rules of the maths, when you divide by 3 on the right hand side, you should divide by 3 on the left hand side. It means this 3 going to cancel this 3. We left with inductive reactance in this side. 16 divided by 3, it is give us 5.3.3, but we forget our SI unit. Our SI unit is going to be ohms. We calculate the inductive reactance. Now, let us go to another question that it is 2.3.3. It says this question to you. Let me show you the question. It is 2.2.3. Is this one? It says, state if the circuit is capacitive or inductive and motivate your answer. We are going to state this circuit, or it is a inductive or a capacitive. Let us go back to our given to check this circuit, it is an inductive or a capacitive. I can say to you, this circuit, it is a capacitive. This circuit, it is a capacitive. Why? Because the voltage drop across the capacitor is greater than the voltage drop across the inductor. If you can check, voltage of capacitor is greater than voltage of the capacitor. That's why we said this circuit, it is a capacitive. That's why we said the circuit, it is a capacitive. Now, let us go to the 2.3.4. 2.3.4, that one is going to need your attention. You need to understand this one. This one you need to understand it. It says, complete the Phasor diagram on the answer sheet. You have answer sheet on your question paper where you are going to complete the Phasor diagram. Let me start again. Complete the Phasor diagram on the answer sheet for question 2.3.4 and show the direction of rotation. And show direction of rotation. That one is going to be 2.3.4. Let me change this one. It's going to be 2.3. It's going to be 2.3.4. We are going to draw the Phasor diagram. Phasor diagram. Our Phasor diagram. Let me show you this. I'm going to explain. Our Phasor diagram is going to be look like this. Now, the thing that you should do, most of the time I tell learners this side they should put as an inductor, and this side they should put as a capacitive side. It is an inductive side and capacitive side. Now, you draw the Phasor diagram. When you draw this Phasor diagram, we are going to use the values that you have, that they give you on an given. Like, for an example, they give us voltage through the inductor is equals to how much? Let us check. Voltage through the inductor, it is 16, which means you are going to put 16 here. You go to voltage through the capacitor. Voltage through the capacitor, which means is 24. It means you are going to put 24 volt. Don't forget SI unit. 24 volt. Now, let us go and check again. The question says to you, the previous question, they ask you this circuit, it is a capacitive or inductive. Now, let us check. We said this circuit, it is a capacitive. If we draw our angle, we are going to put on the side of the capacitive, this side of the capacitor, because we said our circuit, it is capacitive. This one you draw, and you draw the line here. Our angle is here. You have inductive reactance on top. You have capacitive reactance here. You have the phase angle. We don't put the phase angle because they didn't say calculate the phase angle. If we calculate the phase angle or they give us a phase angle, we should put the value of phase angle here. Now, after putting that, we should label it. Here it is the voltage through resistance. Is the voltage through resistance. They give us as 12 volts, which means we're going to put 12 volts. And here it is our total voltage. Our total voltage, it is how much? We calculated total voltage. If you remember, we calculate total voltage here. It means we are going to put the answer of total voltage here, which is 14.42 watt volts. Here it is volts. We left with that current, that current they give us here, an IT on our Phasor diagram. The current is how much? They give us 3 amperes. It means here is going to be our total current, which means it is 3 amperes. Now, there's a question that they ask on, it was trial, this is September, where they say to you, calculate reactive voltage under RLC circuit. The reactive voltage, it's here, where you are going to say the greater VC minus the smaller inductive reactance. It means we are going to say how much the VC is, how much our VC. Let us take it here. VC, it is 24 minus VL, it is 16. Our answer is 8 volts. Is there what? We calculate that voltage here. Now, let me show you this Phasor diagram, how marks that they have. They say to us, we should draw the direction. The direction of this graph is going to be clockwise, as well as the Phasor diagram of a three-phase AC generation is going to be clockwise. When they mark it, they're going to give you a mark for that direction, a mark for voltage, and the mark for phasor, the power factor, and the mark reactive voltage. You got how many marks? It's 1, 2, 3, 4. You got 4 over 4. Sometimes they put it as 5 or 6. Now, let's move forward. Let's move forward with this question paper of 2019 November. We draw the Phasor diagram, we calculate total voltage, we calculate the inductive reactance. Now, if we move forward, let us go to 2.4. Let us check 2.4. I just want to compare 2.4 and 2.3. If you can check, here it is a parallel circuit. Here it is a series circuit. I said this one, it is a voltage divider. All current are equal in a series circuit. Now let's go to the parallel circuit. Here it is a current divider. It is a current divider. It means all voltage here are equal. Current are not equal. Why? Because it is a parallel circuit. The reason is because it is a parallel circuit. Let us read the question first. The question, it says, figure 2.4 below show an RLC parallel circuit consists of a 20 ohms resistor and inductor with an inductive reactance of 30 ohm and a capacitor with a capacitive reactance of 40 ohm. All are connected across a 120 volts and 60 hertz supply. Answer the question that follows. Guys, if you can check our parallel circuit here, they give us our voltage, they give us frequency, they give us resistance, they give us inductive. Check here, they give us an inductive, not inductor. They give us inductive reactance. It is XL. We usually calculate XL, but here they already give us XL inductive reactance. They give us capacitive reactance. They also give us the current through the capacitor. They also give us the current through the inductor. And they also give us the current through the resistor. Our given here, we have 20 ohms resistor. We have 30 ohm inductor. We have 40 ohm capacitive reactance. And we have supply voltage of 120 volts and the frequency of 60 hertz. Of 60 hertz. Now let us go to the calculation where they say calculate. Answer the question that follows. 4.4.1 it says calculate the total current in the circuit. Calculate the total current in the circuit. Do you remember I said to you on your formula sheet there is two formulas that appear under RLC is the formula of parallel circuit and the formula of series circuit. Is the formula of parallel circuit and the formula of series circuit. And formula of parallel circuit and the formula, I just want to show that formula. I want to show you that formula I'm talking about. Here it is an RLC circuit formula. Here it is an RLC circuit formula. We have formula of a series circuit and we have a formula of a parallel circuit. The question says now, let us check this question. The question says calculate here, this question. It says calculate the total current in the circuit. Which means we are going to check the formula under a parallel circuit that is under RLC circuit. Let us check this formula of total current. The formula under parallel circuit RLC, the formula of total current is this formula that says IT is equals to square root of IR squared, IL minus IC squared. Is the formula that we are going to use when we calculate current through the total, when we are going to calculate the total current in the circuit. Now, let us take this formula and calculate. We said it is 2.4, or let me put it here, it is 2.4.1. I said we are going to take this formula of IT, total current, is equals to square root of current through resistance squared plus, open the brackets, current through inductor minus current through capacitor squared. Now, let us go to our giving. Let us go to our giving. Let us go to our giving. Hurry checking in our giving. They say, no, this one is not working. They say current through the resistance. We have it here, it is 6. Current through the inductor. We have it here, it is 4. Current through the capacitor. We have it, it is here 3 amperes. Now we are going to substitute that current. We have it. It's going to be it's going to be current through the resistance. It is 6 squared. Let me start in this side. Sorry. We set our IT. It is equals to square root of IR squared plus IL minus current through capacitor squared. It means current through resistance, it is how much? We have it, it is square root of 6 squared plus, open the brackets, current through the inductor, it is how much? Current through the inductor, it is 4 minus current through the capacitor, it is 3 amperes squared. Here is the current through the capacitor, and here is the current through the inductor. When we calculate here, we use our Casio scientific calculator. The answer of 6 squared plus 4 minus 3 squared is going to be, let me calculate, is 6,08 ampere. It means we have our total current. I said to you, when you calculate, don't forget SI unit. This SI unit, don't forget it. Now, we have our total current. The second question that it is 2.4.2 here. It is 2.4.2. It says, calculate the phase angle. Calculate the phase angle. The one thing that you should know when you calculate the phase angle, you should start by calculating what? The power factor first, and after that, it is where you're going to find what? A phase angle. Let us start with the formula of a power factor first, under the parallel circuit formula. Let us go and choose the formula. The formula of, I said to you, you should calculate what? The power factor first. And the formula that have a power factor is this one of a power factor is equals to current through the resistance divided by total current. Now, let's go and calculate it. Let's go and calculate it. Let us start. I said the formula, it says cos theta is equals to current through resistance over total current. Ne? Now, Our current through resistor, we have it. We have our current through resistor. Yes, we have it. Current through resistor, it is 6 ampere. It means we are going to substitute 6 divided. Total current, we have it. Remember, this, it is a parallel circuit. And in a parallel circuit, current are not equal. It's only voltage which are equal. Now, if you remember well, here in 2.4.1, we calculate what? The total current, which is 6.08 amperes. It means here we are going to substitute 6.08, which is equal to, when we calculate it, it is going to be equal to, let us calculate it. It is 6 divided by 6.08 is equals to 0.98. Remember, I'm going to take 2 digits after a comma because our instruction, read the instructions first. Our instruction says take any 2 digits after a comma. Now, remember, here it is a power factor. And the question says calculate what? The question says calculate what? The question says calculate, let me show you the question. It says calculate what? The phase angle. Here we did not calculate the phase angle. We calculate the power factor. It means a phase angle, it is a theta. Where it's going to be? Theta is cos R minus 1 cos 0.98. We are going to take our calculator, say second function, cos 0.98, not 98, is equals to phase angle. Our phase angle is equals to 11.49. What degrees? What degrees? 11.49 degrees. Now let us move forward, guys. 2.4.3. It says 2.4.3. State whether the phase angle is leading or lagging. Motivate your answer. Guys, you must always try to motivate your answer when you answer the question papers. Now, let us check this 2.4.3, what it says. State whether the phase angle is leading or lagging. Motivate your answer. The answer of this 2.4.3, it should be the phase angle is lagging. The phase angle is lagging. Why? Because the inductive current is larger than the capacitive current. Let us go back to our given. If you want to answer this, let us check. This current, inductive current, is larger than capacitive current. It means if inductive current is larger, then the circuit, it is lagging. Our time is mine. Let's go to 2.5 of question paper of 2019 November. Let us hear what it says. Let us hear what it says. 2.5. It is a resonance. It is talking about resonance. That one, it is very nice when it's talking about resonance. It is a 2.5. Figure 2.5 below. Show an RLC series resonance circuit which consists of a 12 ohm resistor, an inductor with an inductive reactance of 50 ohm, and a variable capacitor, but all connected across a 120 volts and 2000 Hertz supplier. Answer the question that follows. I just want to explain one thing. When they talk about the variable capacitor, do you see this capacitor? This capacitor, it is a variable capacitor. Now, the most important statement that you should check in this question, it is this one of RLC series at resonance circuit. Remember one thing. Under the definition, when they say explain resonance frequency, it's a resonance frequency. It is where inductive reactance is equals to capacitive reactance. It is where XL is equals to XC. It is where impedance is equals to resistance. It is where voltage through inductor is equals to voltage through capacitor. It is where voltage through the resistor is equals to voltage, total voltage. Now remember one thing that is important. It is where inductive reactance is equals to capacitive reactance. I just give you all of the stages where the values are equal. Now let us check this one. They give us a series circuit with a total voltage of 120 volts and the frequency of 2000. Why I say this frequency is 2000? Do you see this K? This K, it means it is multiplied by 1000. It is 1000. It's going to be 2 times by 1000. It's going to give us what? 2000 Hertz. It's going to give us 2000 Hertz, because the SI unit of a frequency is not kHz, is only Hz. That is called Hertz. Okay, they give us 12 ohm resistor. They give us inductive reactance of 50 ohm. Now let us check the question that they ask. The first question of 2.5.1, it says calculate the value of capacitor. Calculate what? The value of capacitor when the circuit resonance at 2000 kilohertz. Now we are going to calculate what? The value of capacitor. Let us start with the formula of a capacitive reactance to find the capacitor, because they give us what? Resistance, they give us inductive reactance, they give us frequency, they give us what? Total voltage. Let us start. The formula of capacitive reactance is equals to 1 over 2 pi times by frequency times by capacitor. Our unknown, it is capacitor. Our unknown, it is capacitor. Now let us check. According to the given that they give us, we have two unknown. It is a capacitor and capacitive reactance. It is a capacitor and capacitive reactance. Now we should work out this thing of two unknown. But remember this statement, at resonance. I said to you, at resonance, what happened? Inductive reactance is equals to capacitive reactance. Do you remember when you check our given, they give us inductive reactance? It means if inductive reactance is equals to capacitive reactance, this 50 Hertz, it is also equal to capacitive reactance, because at resonance XL is equals to XC. It means here under XC we are going to substitute what? 50 Hertz, or 50 ohms is equals to 1 over 2 pi times our frequency is 2000. I said is 2000 because of this K, multiply by our capacitor. It means it is an unknown. It is an unknown. According to the mathematical rules, any number is over 1. Here we are going to make a cross multiplications. A cross multiplication, it means This is going to multiply by this. This is going to multiply by that. Let us do it. It's going to be 50 multiplied by 2 pi multiplied by 2000 multiplied by C is equals to this multiplied by that. 1 multiplied by 1. Which means we are going to find our unknown, that it is capacitor. We are going to divide. We want capacitor. We are going to divide with all numbers that we don't want in this side of a capacitor. Which the first number it is this 50. Why we divide by 50? We want this 50, cancel this 50. Multiply by 2 pi. Why we divide by 2 pi? We want this 2 pi, cancels this one. Divide by 2000. Why? Because we want this, cancels this. Now, according to that mathematical rules, the numbers that you divide on the right hand side, you should divide by them on the left hand side. It means we are going to divide by 50 multiply by 2 pi multiply by 2000. Let us check. This 50 cancels this. This cancels this. This cancels this. In this side, we left with capacity. But in this side, we left with 1 multiply by 1 divide by 50 times by 2 pi times by 2000. It gives us the answer of, let us calculate it, the answer of 1,59 microfarad. 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 This is contained 4 marks. Don't forget SI unit. Always when you calculate, don't forget SI unit. Now, let us go to another question. That is says, it is, oh, let me put it up. Another question, let me show you the question first. The question is says, 2.5.2, calculate the value of current in the circuit. You are going to calculate the value of current in a circuit. And you should remember, I said this is a resonance stage. It's different with the series circuit and the parallel circuit that we have previous. This one is at resonance stage, where it is 2.5.2. This 2.5.2, we calculate current, we calculate the value of current in the circuit. I can say to you, the value of current in the circuit, it is total voltage over Z. Total voltage over Z. Here we come again. Elena asked, Mener, here you said the formula it is total voltage over impedance. But in our question, we don't have an impedance. Check. We have total voltage, we have frequency, we have resistance, we have inductive reactance. But we don't have impedance. There is no way that we can find our impedance here. But remember one thing. I said to you, this stage is at resonance. At resonance, remember this thing. Resistance is equals to impedance. Now, let's go back and check in our given. We have a resistance. Here is our given. We have resistance of 12 ohms. It means we said at resonance, resistance is equals to impedance. It means here, our impedance is going to be 12 ohms. Now, we are going to say total voltage, it is how much in our given? Total voltage, it is 120 watt volts. It means we are going to substitute 120 volts divided by 12, which is give us how much? It's going to give us 10 watt. 10 watt. 10 amperes. It's going to give us 10 amperes because I said to you don't forget to put SI unit. Always when you calculate, put an SI unit. Now, let us go to another question, which is 2.5.3. It says, state how the current will be affected if the value of the resistor is doubled. Guys, this one, without going anywhere, if we double the value of the resistance, the current is going to be half. Is going to be half, because when the impedance or the resistance increase, the current is going to decrease. But if the frequency is increase or decrease, the current is going to be dropped always. Like in this question, when they say state how the current will be affected if the value of resistance is doubled, it means that current is going to be dropped. If resistance is doubled, current is going to be half of that doubled. Now let's move forward, because this one is the easiest question. The 2.5.4, it says, list 3 characteristics of an RLC series circuit at resonance. I mentioned that earlier. It says, list 3 characteristics of an RLC series circuit at resonance. I mentioned that earlier. I said to you, the one that I sing all the time when I talk about resonance stage. The first one, I said at resonance stage, inductive reactance. Let me write it to you. I said to you, at resonance stage, inductive reactance is equals to capacitive reactance. XL is equals to XC. Even in this calculation, we use this statement. The second one, I said impedance is equals to resistance. If you can check even here, we use that. Resistance is equals to impedance. The third one, voltage through resistance is equals to voltage, total voltage. This one, guys, if you remember well, I talk about in series circuit, current are equal, voltage are not equal. But if you can check at resonance in series circuit, voltage are equal. But in parallel, at resonance, current are equal. Let me give you another one. It is XL is equals to XC, impedance is equals to resistance, voltage through resistance is equals to voltage, total voltage, voltage through inductor is equals to voltage through capacitor. They say 3, but I already give you 4 now. The other one, it says current is equals to what? Max is maximum. Current is equals to maximum, okay? And even impedance is equals to, if the current it is maximum, remember I said when the resistance is doubled, current is going to be half. It means if the current is maximum, the impedance is going to milli. Is that all, guys? Okay, we can say theta is equals to 0 degrees. There are so many. Up to so far we end with that question paper of 2019, but I just want to add some stuff with RLC circuit using another paper, using any other paper that I can find here. Okay, here is the paper. Using this question paper. I don't know where it's coming from, this paper, but I'm gonna use it. Let us check this question, guys. It is an easiest question. It is a basic question that we use. It is an easiest question and a basic question. I'm going to give you this. I'm going to give you this circuit. Let us start with 2.2. This 2.2 is the basic or standard questions of RLC circuit. I don't want to say it's the simplest, but it's the easiest questions. This question, is a series circuit, and remember I said to you, in a series circuit what's going to happen? All current are equal. If you can check here, they say to you, refer in the circuit diagram figure 2.2 below and answer the questions that follows. The questions that follows, okay, they give you the resistance of 25 ohms there. It is not the inductive, it is an inductor because it is not XL, it is only L, which means it is an inductor of 44 millihenry. They give us the capacitor of 120 microfarad. Let us try to calculate this faster and go to the next chapter. I'm going to be a little faster in these questions because of time. Now, let us start with 2.2.1. 2.2.1. I said to you we have a formula sheet of Rlc circuit. It says calculate what? Calculate the inductive reactance. When they say calculate the inductive reactance, it means you calculate what? XL. It is an inductive reactance. If you can check here in your formula sheet, I just want to show formula sheet first. If you can check here in your formula sheet, it is XL is equals to 2 pi FL. Which one is XL is equals to 2 pi FL. F stands for frequency, L stands for inductor. Now, here we are when you answer it. Here we are when we answer it. We are going to say XL is 2 pi times our frequency is how much? They give us a frequency of 60 Hz. It is 60 times they give us the inductor of 44 millihenry. And remember, the SI unit of inductor is only Henry, not millihenry, which means we are going to say it is 44 times by 10 exponent minus 3 times by, oh, not times, I'm sorry, it's n there, it's not times by. When you take your calculator, you calculate this, you are going to find your answer is 16,587 watt. SI unit of ohms, because we calculate what? Inductive reactance. And inductive reactance, remember, it's belong under and impedance. Now let us go to 2.2.2 where it says calculate the capacitive reactance. Formula of capacitive reactance, if I can show you the formula sheet. Here it is in the formula sheet. It is 1 over 2 pi FC. It's going to be XC is equals to 1 over 2 pi FC. It's 1 over 2 pi. Our frequency it is how much? Our frequency it is 60 Hz multiplied by our capacitor. It is 120. Here it is 120 watt microfarad. Our capacitor it is 120 times by 10 to the power negative 6. Our answer it is let me calculate it. Our answer it is 22,105 watt ohms. Now let us go to the another question. Obviously going to be an impedance. Calculate impedance of the circuit. When they say calculate the impedance of the circuit, the formula of impedance, we are going to find it here. Formula impedance is this one of Z. This one is this one of Z is equal to R squared plus XL minus XC. Impedance is, our impedance is square root R squared plus XL minus XC squared, which means our resistance is how much? Our resistance it is 25 squared plus our inductive reactance it is, we calculated it is 22,105 minus our inductive reactance, it is 16,58 watt squared. Now our answer, it is 25,6 watt ohms. Guys, do you see we calculate impedance and capacitive, we calculate inductive reactance and capacitive reactance because we want to find what? An impedance here. Now let us go to another question that says calculate what? Let's go to the questions. The other question, the total current flow through the circuit. When they say calculate the total current flow through the circuit is 2.2.4. It is IT is equals to VT over Z. Most of children ask why we use impedance here instead of standard formula that we did in grade 10, that is a VT over R. We said impedance because impedance, it is the total, is contained resistance. The SI unit of resistance is ohm, is contained the inductive reactance, and the SI unit of inductive reactance, it is ohms, is contained the capacitive reactance, and the SI unit of capacitive reactance, it is ohm, which means we combine all these ohms as a total what resistance is going to be 120 divided by 25,6. Our answer, it is 4,69 watt amperes. We finish. Now it is finished. This is the standard question that they ask RLC. When we teach learners, we start with this one in grade 11. Try by all means to win this 40 marks, because I think this topic is the easiest topic that we did it from grade 10 up to grade what? Up to grade, from grade 11 up to grade 12, not grade 10, sorry. Learners, now we are going to go to the next topic, which is three-phase AC generation. This topic consists of theoretical questions as well as the calculations. Theoretical answers should be short and to be pointed. Sorry. Short and pointed. Now, I choose some possible questions of theoretical, which is a kilowatt hour meter, watt meter. Sorry. It's a kilowatt meter and power meter. Now let us start with the power meter. The question that they most of the time ask, they're gonna say state the functions of the following meters. Here we talk about only meters under three-phase AC generation. We start with the theory and we went to the calculation later. Now let us start with the power factor meter. It says the power factor meter is used to measure the power factor used. It is how to define a power factor meter. Now let us go to remember I talk about 3 meters. Let us go to the kilowatt hour meter. A kilowatt hour meter, it is used to measure the amount of electrical power consumed by the load over a certain period of time, or measure the energy. When you talk about the load is a heater, stove, kettle, like it means that thing, it is a load. Even the motor, it is a load. Let us go to the last meter that we have. The last meter that we have, it is an watt meter. Watt meter, it is a meter is used to measure the amount of electrical power consumed by the load. But be aware, watt meter does not measure the energy. Now, another three-phase AC generation, we have the other possible questions, that it is list 3 advantages of a power factor improvement for the consumer. The one that we can say it is a less current use. The other one is gonna be reduced monthly bill. The other one is gonna be reduced heat generated by equipment that could then last longer. Reduced maintenance. Here we have 3 advantages of a 3-phase AC generation over a single-phase AC generation. I'm going to read it fast. It's going to be 3-phase generator is similar frame size, has 3 times the power of a single-phase generator. The 3-phase power is cheaper to generate than single-phase power. The 3-phase generator can supply power to 3-phase and single-phase. We have the losses occurring in the transmission line. It is a copper losses and iron losses, because transmission line is used copper most of the time. They're gonna say sometimes explain the efficiency. The efficiency is the ratio of the output power to the input power. We can use as a formula. Here guys is the 2 different things. We have the difference between a phasor diagram and the waveform. There is a difference between a phasor diagram and the waveform. Here, this side we have a phasor diagram. This side we have a waveform. And the phases between the lines, it is 120 degrees in this phasor diagram. The angle between the phases, it is 100, or the distance between it is 120 degrees. The direction, it is clockwise. Let us check, because guys here most of the learners make a mistake because of a mistake that they see in the textbook. In the textbook, they give us a wrong lines. They started with here. They say this line, it is blue. Check. There, this line, it is red. V line 1. V line 2 is going to be yellow, and V line 3 is going to be blue. I think it's better to go to the calculations straight. Now guys, here under calculations, check. Remember, under AC generation, transformers and motors, we deal with 3 boys. I call them boys. It is a star and delta. It is a star and delta. It is a star and delta. If you can check, in star, line current is equal to phase current. Line voltage is equal to square root of 3 times phase voltage. In delta, it is line current is equal to square root of 3 times line phase current. Do you see current in star is equal to phase current, but in delta is not equal current? Do you see voltage in delta, V line is equal to V phase, but in star, V line is not equal to V phase? Now, I have some calculations here at the PowerPoint, but I think I'm going to do down. Skip this one of a PowerPoint on the screen. I'm going to take the question paper of 2019 for the calculations. I'm going to take the question paper of November 2019. Question paper of November 2019, where it is started by a 3.6. Where it is started by 3.6. Let us check this 3.6, what it says. It says a 380 volts 3-phase star connected. Remember, when they talk about the connection, your connection, it is already what? Star connection. It is already what? Star connection. It means in star, I line is equals to I phase, and V line is equals to square root of 3 times by V phase. Remember that thing, because I show you formula at the beginning of the presentation. Now they say to you, A 380 volt 3-phase star connected AC motor, I said it's a star connected AC motor, has an output power of 25 kilowatt, and it operates at a lagging power factor of it operates at a lagging power factor of 0.87. The efficiency of the motor, it is 85%. Guys, I advise learners most of the time read question twice before answer. A 380 volt 3-phase star connected AC motor has an output power of 25 kilowatts, and it operates at a lagging power factor of 0.87. The efficiency of the motor is 85%. We have line voltage, efficiency, power factor, and output power. The first question it says it is 3.6.1. It says calculate input power. Calculate what? The input power. Now, earlier I showed you how to use the formula sheet. You have a formula sheet and all formula. You have a formula sheet and all formula. I said to you, now we do 3-phase AC generation. Here it is the formula sheet of 3-phase AC generation. You can check it's the 3-phase AC generation. Now the question it says calculate what? The input what? Power. If we calculate the input power, we are going to check the formula or under the 3-phase AC generation. We have in our given, we have output power. We have output power which is 25 kilowatts. We have efficiency. We can take or choose this formula of efficiency is equals to output power over input power. It says efficiency is equals to P out over P in multiplied by 100%. Now, to make it this easier, they give you an efficiency of what? They give you efficiency of 85%. If they give you the efficiency of 85%, the one thing that you should do is to divide that efficiency by how much? You are going to divide your efficiency by 100 because it is 100%. Ne? You are going to divide it by 100 because it's 100%. But you can continue without dividing that efficiency if you like. Okay, let us check. We set efficiency, it is 85. Output power, it is how much output power? Our output power, it is 25. Let me show you our output power. Our output power, it is 25, which means our output power is going to be 25,000. Because our output power, it is 25 kilowatts, and the SI unit of power is only watts, not kilowatts. That's why we multiply by 25,000. Our input power, it is an unknown, multiply by 100. You multiply by 100. Now, let us go to the answer straight. If you multiply this, because we are going to make cross multiplications. Okay, let me make it. We are going to say P in times is going to be input power times by 85 is equals to 25,000 multiply by 1 multiply by 100, which means input power is going to be 25,000 divide by 80. Oh, do you remember? We divide here. Sorry. Divide by 85 times by 100 what? 100%. The answer of input power is how much? the answer of input power is going to be 29.41 watt. 29.41 kilowatt. Or other answer my calculator give me, it is 29.411,7 watts. Check the difference here, we put kilowatts and here it's only watts because the SI unit of input power or a power, it is only watt, it's only watts. Now let's go to the next question. The next question, it is says calculate the line current. Calculate the line current. Guys, check this one. It is 3.6.2. When we calculate the line current, we go to the formulas of a three-phase AC generation. I've choose this formula because this formula it is I choose this formula because this formula it is a square root of 3 times by V line times by I line times by what? Cos theta, and we also have input power we already calculated. We are going to have only one unknown, which means it's IL. I said I'm going to choose this formula of input power is equals to square root of 3 times by line current times by line voltage times by power factor. Remember guys, you are allowed to use the phases because the difference between phases and the lines, the phases we don't put the square root of 3, but the lines we put the square root of what? Of 3. Now let us calculate this. Input power, it is how much? Our input power, it is, I'm going to take this one of watts, not kilowatts. It's going to be 29,411.7 is equals to square root of 3 multiplied by unknown line current multiplied by voltage. We have it. They give us V line, which is 308. They give us power factor, which is 0.87 lagging. Here we are going to say V line multiplied by I line multiplied by 308 multiplied by power factor is how much? Our power factor, it is cos theta, that is 0.87. If you divide this side by square root of 3, times by 380 times by 0.87. Why we divide? We want this cancels this, this cancels this, this cancels this. We should left with what inside? I line only. This side we are going to divide by root 3 because we divided on the right hand side. We are going to divide by 308 divide by 0.87. Our answer of current is going to be, let me calculate it first, is going to be okay, it is 51.36 watt amperes. You finish to calculate what? The current, line current. Let us check last question what it says. Our last question, what it says. Calculate the phase current. Remember, our connection, it is star connection. If our connection, it is star connection, we are going to say, let me write it here. It is 3.6.3. We are going to say, in star, line current is equals to phase current. Here you already calculate what? Line current. And the question want what? Phase current. And in star, line current is equals to phase current. It means your phase current is the same answer that you got there at the line current. The answer of 51.3 6. That question is easier as that. Now, let's move forward and check the questions that belong under subtopic of wattmeter. Subtopic of wattmeter. Under a subtopic of wattmeter, it is where we are going to calculate what? Let us check. It is where we are going to calculate the power. Now, let us start with that questions of what? Of wattmeter. 3.7. 3.7. Refer to the figure 3.7 below and answer the question that follows. Given. They give you wattmeter 1 of 14,000 watts. Power, the second power of wattmeter is 18,000 kilowatt. Now we have power wattmeter this side and power of wattmeter in this side. Let us go and check the question what it says. Let us check the question what it is says. 3.7.1. Identify the method used in figure 3.7 to measure the power to the load. If you identified as this thing, we have oddmeter and wattmeter. The method that you use is a 2 wattmeter method because we have wattmeter 1 and we have wattmeter 2. The answer it is 2 wattmeter method. Let us go to 3.7.2. The question says, calculate the total power used by the load. You are going to calculate the total power that used by the load. The formula of total power, it is PT is equals to, even if you can check it on the formula sheet, it is PT is equals to P1 plus P2. If you are having a 3 wattmeter, wattmeter 1, wattmeter 2, and another wattmeter here, our formula is going to be P1 plus P2 plus P3, but we only have 2 wattmeter. It means our formula is going to be P1 and P2. Let us check our P1. It's how much? Wattmeter 1, it is 14 plus wattmeter 2, it is 18. Our answer, it was 32 watt, 32 kilowatt. Why I'm not saying 32,000 watts? Because I take 14 as kilowatts, I have take 18 as kilowatts. Now my answer should be kilowatts. But if I was saying 14,000 plus 18,000, it should be 32,000. My answer should be 32,000 watts. Now, let us go to the next question, which is calculate the power factor of the system. Remember, I showed you earlier the formula of power factor. The formula of power factor is cos theta. That thing, it is a power factor. Now, let us go back and check under this questions formula sheet of wattmeter. Under a formula sheet of 2 wattmeter or 3 wattmeter, we don't have a formula of power factor, but there is a way that we can find the power factor, the cos theta, because we have tan theta. Let us use this formula of tan theta. This formula of tan theta, it is say, remember we want wattmeter. It is say tan theta is equals to square root of 3. Let me show you the formula. It's this one. Power 1 minus P2 divided by P1 plus P2 brackets. Now, our life is easier. It's 3. P1 is how much? P1, remember, we have it. P1, it is 14. Minus P2 is how much? P2, it is 18. 18. Divide by what? P1 is how much? It is 14. plus what? Plus 80. If you take calculator, do this, it's going to give you minus 0,222. It is what? Tan theta. Now the question says want what? Power factor. Now we have tan theta. We can want theta here by saying tan arc minus 0,22 in the brackets. That one, theta, is going to give us what? Is going to give us 0,98. Is going to give us, I'm sorry. It's tan theta arc negative 22. Now, our answer here, or theta, it is how much? It is minus 12,41 what? Degrees, because we calculate what? Theta. And remember, the question says power factor cos theta. Now we have theta. We can say cos, instead of putting this theta, we put this value of negative 12,41, which is negative 12,41, close the brackets. The answer is giving us 0,98 watt. 980. The power factor is equals to 0,98. You find your power factor as easier as that. Now let us go to another paper first. Let's check another paper, similar question on another paper, because I've got two different papers here. Okay, guys, I have the question paper here. It was three-phase AC generations. I'm going to be faster because I already done it. Let us check this question. It says, refer to the figure 3.4 below and answer the questions that follows. They give us wattmeter 1 of 5,000 watts, and they give you the wattmeter 2 7.5 kilowatts. It means first thing that you should multiply by, you should remove this kilo. When you say 7.5 multiplied by 1,000 is going to give you the wattmeter 2 of 7,500 watts. Now you can calculate. The question are similar as the question that we calculate in the question paper of 2019, because the first question is says it is 3.4.2, where it says calculate the total power of the three-phase system. It is where we are going to say PT is equals to P1 plus P2, or you can say wattmeter T is equals to W1 plus W2. Let us go to the next. Let's follow the second one. Calculate the power factor of the system, which is power factor is that one of cos theta is equals to unknown. We don't have to find it, but we have the ways. We don't have it, the formula of it, but we have the ways of finding it by using this formula of tangent theta is equals to square root of 3 over P1 minus P2 divided by P1 plus P2. There's a way of finding that answer when you calculate the power factor, because after getting the answer of this tan, you are going to say minus 1 theta. Minus 1. You put the answer that you got here. You got what? Theta, and we substitute theta here. Guys, because of time, I should rush this one. Guys, now we are doing the third topic, which is three-phase transformer. I'm going to be a little quick with it because I just want to rush to that topic that contains 60 marks. In this topic, contains theoretical questions as well as calculations. Theoretical questions are normally a challenge and many learners struggle to answer it properly. That's why I make some notes for it, the definitions and the operations. A learner must read all the question with understanding before answering the question. Theoretical answer should be short and to the point. Now, I have chosen some theoretical question that it's possible because I just want to take your mind back in this topic. The most important aspect to remember about the transformer is its basic operation principle. It's important to note is that a transformer operation is based on the principle of mutual inductions. Now, let us check what it says. When an alternating voltage is applied to the primary windings, an alternating flux is created in the windings. This flux will link with the secondary windings through the magnetic path of the ion core of the transformer, inducing in it an EMF of the same frequency. Now, we have this connection of a transformer. We have the three-phase primary windings and the three-phase secondary windings of a three-phase transformer can be connected in different way to form a single unit. Now, when we talk about the three-phase, we take three identical transformers and combine it by connecting delta and star, combine it as a one three-phase transformer. If you take three identical transformers, or it form a three-phase transformer because we are going to connect it in delta or star. Let us check our connection. The first connection that we should be used, because we have a secondary transformer and primary transformer, it is a delta star connection. In our delta star connection, use to extensively as step-down transformer in distribution system where 4-wire system is required to supply both single and a three-phase voltage. We have another connection that you call it a star delta. The star delta is used as up-down transformer in high voltage supplying lines. We have the other connection, which is delta, is used in a heavy industries where a high power is essential. We have the last connection, which is star, used a lot because of harmonies in the secondary, use mainly for interior wiring of premises. Now, the connection that I'm talking about, look like this, is the connection of the primary side, which is delta, and the secondary side, which is a star. If you can check, when you talk about the delta is going to be what? End to start, end to start, end to start. And a star connection is going to be end to end and end to end. Now, let us go to the losses of a transformer. And the losses of a transformer. Under losses of a transformer, we have a copper losses, we have iron losses, we have hysteresis losses, we have eddy current losses, dielectric losses, and we have stray losses. Let us check some few losses. I'm not gonna read it all of it. Let us check copper losses. Losses due to the resistance of a copper wire. Because you know electrical wires, we mostly use the copper. Let us check the electric losses. It's the losses to the circulating current in the lamination of a core. If you remember, when you do a single phase transformer, the smaller transformer of a TV and radios, we use I lamination and E lamination. That I and E, we should laminate it by thinness, sometimes if they're plastic. Now, transformer. Transformer can be vary in size from very small to very big. The bigger the transformer, the more expensive it will be. Okay? Now we have the following formulas are important, and even when given, you need to know where to use it. Check. Under a three-phase AC generation, I was talking about star connection and delta connection. Even under three-phase transformer, I'm also talking about star connection and delta connection. And in star, V line is equals to square root of 3 times by V phase. I line is equals to I phase. Under a delta connection, V line is equals to V phase, and I line is equal to square root of 3 times I phase. They are a formula of apparent power, reactive power, and true power. Now, let us check. Transformer equations. The primary and the secondary voltage are directly proportional to the number of turns on each coil. The primary and secondary current is inversely proportional to the number of turns in each coil. The primary and secondary voltage are inversely proportional to the current. Let me show you what is this mean. If you remember, when I'm talking about the primary and secondary turns, and we have this formula of a transformer, which means it's number of turns in primary divided by number of turns in secondary. In secondary is equals to voltage in primary divided by voltage in secondary. If we work inversely, it means when you talk about is current in secondary divided by current in what? In primary. Do you see the difference? The current secondary is on top and the primary is down. Okay? Now, there are three losses that can occur in transformer. I already mentioned it's a eddy current, ion losses. It is an hysteresis. It's the same as that one. Let us check this one. Let us check this one. Explain how losses are minimized in a transformer with regard to the hysteresis losses and eddy current losses. This one is the question paper of 2019. Is the similar with the losses that I give you on top. Name two types of cooling method for a dry transformer. We have neutral air. We have neutral air following over transformer. It is air force cooling with the air of fans. Now, state three factors that may contribute to excessive heating of a transformer. Insufficient circulation air for cooling of a transformer, insufficient oil in which the transformer is immersed, constant overloading, internal fault overloading. List three external conditions that may cause transformer failure. Is the same thing that like that they change equations. Now, describe how the phase current is induced in the secondary windings of a transformer. How to induce the secondary windings of the transformer. I make a 2 point here. The first one, you can say, when an alternating voltage is applied across the primary windings, an alternating current will flow, creating a magnetic field in the magnetic core of a transformer. This magnetic field will link with the secondary windings. You are going to link it with the secondary windings through the magnetic core inducing the EMF of the same frequency. The induced EMF is responsible for inducing the secondary phase current. Now, always try to draw the circuit. When you do calculations, always try to draw the circuit to make your solution easier. I made an example. Here there is a circuit of a three-phase transformer. We have what? We have a primary side and we have a secondary side. We have power on the secondary side, power factor on the secondary side. We have line voltage on the secondary side, and this side we have line voltage on the primary side. Let us go to calculations straight. Now, let me do one paper of 2019 November of three-phase transformers. The question was like this. Let me show you this question. It is 4.7. A star delta, remember I said to you, focus on the connection. Star delta, it means the primary side it is star and the secondary side it is delta. A star delta connected transformer has 60 turns. It means the number of turns it is 60 in the primary windings and 80 turns in the secondary windings. If you can check, the primary turns is bigger than the secondary turns. It means that one is the, if a primary is larger turns and the secondary is smaller, it is step down transformer. 80 turns in the secondary windings. The transformer is connected to the 6 volt supply. They give you number of turns in primary, number of turns in secondary, and they will also give you line voltage. The first question it is says, calculate, let me calculate here. Calculate what? The turns ratio. The turns ratio. The turns ratio is equals to, turns ratio is equals to, we talk about turns, number of turns. Number of turns is n. Turns ratio is equals to number of turns in primary divided by number of turns in secondary, which is 60 turns in primary divided by 80 turns, I'm sorry, 80 turns in secondary. Now we are going to say 600 divided by 80 is giving us 7.5. Because it is ratio it is 1:1 scale, like EGD scale, 1:1, 1:2. It means we are going to say 7.5 to 1, but there is no ratio that say 7 point mamma or 2 comma mamma. We are going to round off this 7.5. Our scale, our turns ratio is going to be 8:1. That it is a final answer. Now the second question, it is says, which is 4.7.2. It is says the primary phase voltage. You calculate what? The primary phase voltage. Remember our connection, it is star delta. They say the primary phase voltage. When they say you calculate the primary phase voltage in star, they say a primary is star, and in star V line ya primary is equals to square root of 3 times by V phase ya primary, ne? Now let us check. We have line V line ya primary, it is 6 kilovolts. Do you remember I said to you, remove this K, which means going to be 6,000. The voltage line ya primary, it is 6,000. When you substitute, divide by square root of 3 times by V phase is how much? It's V phase of primary. It is an unknown. We are going to divide 3 this side. If we divide this side by 3, we are going to divide this side again with 3. This cancels this. We left with V phase of primary is equals to 6,000 divided by square root of 3. Your answer, which is how much? Which is your answer? It is going to be. It's going to be 6,000 divided by square root of 3 is giving us 3464.10. The SI unit is going to be what we calculate voltage is going to be volt. Now let's go to another question. When it says calculate what? The secondary phase voltage. Calculate what? The secondary phase voltage. Do you remember we have number of turns in primary, we have number of turns in secondary, we have a voltage, line voltage in primary, and we have line voltage, phase voltage in primary. Now let us take one formula and calculate this. Now hurry. We are going to say V phase of primary divided by V phase of secondary is equals to number of turns in primary over number of turns in secondary. Ne? You can make subject of the formula, or you can substitute. You can substitute, or you can make subject of the formula. Let us make subject of the formula. Is going to be V phase secondary, this multiplied by this and this multiplied by this is equals to V phase of primary multiplied by number of secondary turns. This multiplied by this is this. This multiplied by this, it was here we have number of primary. We are going to divide by number of number of primary, number of turns in primary, and this side we divide by number of turns in primary. This cancels this. That's why I said to you we left with V phase of secondary is equals to V phase of multiplied. We left with V phase of secondary is equals to V phase of primary multiplied by what? You multiplied by number of turns in secondary divided by number of turns what? In primary. Which means when you substitute is going to be we got here our V phase in primary, it was 3464. It is here, comma 10 multiplied by number of turns in secondary, it is 80 divided by number of turns in primary, which is 600. Our answer, it was 461 0.33 volt. Remember, I said to you when I start this presentation, always put SI unit. Always put SI unit. And now, I just want to check another paper quick and move forward. Another paper quick and move forward. Now, there's another paper here. There's another paper here that it says, to show you some. There's another paper here. There is another paper here. Let us check this paper. It is 4.6. If you can check this paper, they say a 20 kVA. When they talk about kVA, it's an apparent power as delta star, which means it's a primary, it's a delta this time, and the secondary is star. Transformer has a primary voltage of 6 kilovolts and a secondary voltage of 1000 volts. The losses amount of 160 watts and the power factor is 0.8. They say apparent power, it is 20 kilovolts amperes. Line voltage in primary, it is 6000, and line voltage in secondary, it is 5000 volts. The power losses is 160 watts. Power factor is 0.8. Now, let us check the question and be faster. I'm going to calculate it faster. Now, it is 4.6.1, where the question says, calculate the secondary line current. Calculate the secondary what? Line current. If you calculate the secondary line current, we are going to use this apparent power. Apparent power is basically on the primary and on the secondary. Apparent power square root of 3 times by voltage at the line on secondary times by current at the line on secondary. Let us check. Our apparent power, it is how much? Our apparent power, it is 20,000. If you can check. The apparent power is 20,000 is equals to square root of 3 times by line voltage in secondary. Our line voltage in secondary is how much? Here it is line voltage in secondary, it is 500 multiplied by line current in secondary. It means we are going to divide this side by root 3 multiplied by 500, because we want this cancels this and cancels this. Ne? The same thing that we did on the left hand side, we should do on the right hand side. We are going to divide by root 3 times by 500. Now, if you left with line current at secondary is equals to 20,000 divided by root 3 times by 500, your answer, it is going to be, your answer is going to be 23.09 watt amperes. 23.90 amperes. Now the second question, let us check. It says calculate the ratio of calculate the transformation ratio. It means it's 4.6.2 where you calculate the transformation ratio. Remember when we calculate the ratio last time, our ratio it says V Phasor primary divided by V Phasor secondary. But if you can check, we don't have it. We don't have these two. Now the first thing that you should do, we should calculate what the phase voltage of secondary. How we are going to calculate it? Remember the question says the secondary side, it is a it is what? It is a star, and the primary, it is a delta. Remember, in star, IL is equals to what? I phase. Ne? Now, let us do this. Let us do this. In our primary side, it is, our secondary side, it is star. And in star, V line, in star, let me say, V phase of V line of what? V line of secondary, because we calculate secondary side, is equals to what? Square root of 3 times by V phase of what? V phase of secondary. Remember this formula. The formula is the formula of delta and star connection. Now, if you can check our question here, question it says the secondary side, it is a star, and in star, V line is equal to square root of 3 times by V phase. That's why we use this formula. Now we have V line as secondary, we have square root of 3, we don't have V phase of secondary. The V line of secondary, it is how much? The V line of secondary, it is 500 is equals to square root of 3 times by V phase of secondary. We divide by root 3. We divide by root 3. This cancels this. It means V phase of secondary is equals to how much? Is equals to 288.68 volts. Now, let us calculate this ratio. It means when we calculate this ratio, we have V phase of primary, which is 6000 divided by a secondary. V phase is 288.68, which is equals to 20.78 to 1, which means is 21 to 1. We calculate that ratio of a transform. Now we can go to the another question. We can go to another question, which is the efficiency of the transformer. Calculate what? Efficiency of a transformer, or the input power. Let us start with the input power. 4.6.3. .3, where you calculate the input power. The input power is equals to a square root of 3 times by IL times by VL times by what? Times by cos theta. Now we are going to say, let me finish first. Square root of 3, 500 multiplied by 23.09 times by 0.88, which is 7.596,94 watts. That is 0.94 watts. The last question is the question of the efficiency, that is say P of input minus power loss divided by P of input power. It means we're going to say 2000 minus 160 divided by 20,000 is going to give you, or multiply by 100%, is going to give you 99.2%. Guys, the lesson of today is end there because of time. We'll see you next time.